Thank you, Casey. Thank you, Casey. It's really a pleasure to be here speaking at the first, is it going to be annual, Casey? I don't know. The first SEC conference. As the title shows, I'm going to be talking about some fuel types that we've made over the years. And there'll be some conventional ones that we think we've made some refinements to, and some novel ones that we believe we are some of the first to have made. So there'll be a mix. First, I want to talk about bio-oil, which is what we're going to make these fuels out of. Bio-oil, you can see it's a highly viscous material. It's made by pyrolysis reaction, which is thermal degradation in the absence of air. We have a 3 liter per hour reactor that we currently make these test volumes with. I'm not showing that because I want to keep the emphasis on the fuels. Now, this is made at 500 degrees C normally, and you don't get the nice gas that you get with syngas at 800 or 900 degrees. You don't get some pure carbon, hydrogen, oxygen type chemical gases that you'd like to get. You get a collection of many, many compounds, and it's water-based. Now, whoever came up with the name bio-oil should be harshly punished. Because every time I go somewhere and talk to anybody in the lab, it takes me about 10 minutes to convince them this is not an oil at all. This is a water-based solution, more or less an emulsion that has hundreds of compounds. They've identified 400, but you can count on any one bio-oil having 100 to 200 compounds. It's quite a recalcitrant liquid. It contains 25 to 30% water. We generally pyrolyze at about below 10% at 8%, 7% very often. But when it explodes the cell wall in these pyrolysis conditions at 500 C, a lot of H's and O's get back together and they make, unfortunately, a lot of water. So it makes it very recalcitrant compound, which is what's made it a more than 30-year research project so far for people. We have highly oxygenated compounds, and that's really the negative property that causes all the trouble. So we have 45 to 50% oxygen. This causes high acidity, aging problems, rapid polymerization over time is basically what that is. It's not immiscible. It's immiscible with petroleum-derived fuels because it's water, really. It's water-based. It has a pungent odor. They thought about using it as an adhesive a few years ago in wood products, and the workers in the industry quickly disabused them of that prospect. It's not very good smelling. It has a low energy density, 35 to 40%. You'll see we have one here. One of our samples had pretty high moisture content, and you'll see a little over 16 megajoules per kilogram value. So with all that water in it, one of the things that you want to do when you convert these fuels is get an aqueous fraction, and that's what's traditionally done. Now this olefination is a novel method that we developed at MSU. We add an olefin. Most of you probably know olefins are refinery byproducts. They're used to make chemicals primarily, and they're a little cheaper than adding a hydrocarbon like that we use at the pump. And they act differently as well, and they help you with the esterification process. So we get a relatively high value energy boiler product. It will never become a transportation fuel because we leave a lot of the oxygen in it. We require for this an addition of a relatively low percentage of alcohol, 20%. We get an aqueous fraction, as I said, which is very good. It allows you to pour water off. And without that, you've got a problem. This is the reactions that you get with this. You have bio-oil has a high percentage of carboxylic acids reacting the olefin over an acid catalyst. You can either use, we've used a homogeneous catalyst, and we also use heterogeneous catalysts in an autoclave at this point, and we get esters and an alcohol with the olefin over the acid catalyst gives you ethers. So it adds, there is a belief that we get some conversion with the olefins of water to alcohols. However, that needs to be tested, and it's not a great deal. I hope you can see this. The mass balance is shown here, where we get 6% of gas, 5% of char. Here's the water we get to pour off, fortunately, 27%. And here's the oil, 62% yield of olefinated bio-oil. So that's a satisfactory yield. We wish it was a transportation fuel, not a boiler fuel. But this is the only time I'm going to tell you, I do show raw bio-oil properties other places, but I'm not going to go over and over it. I'm just going to show you just what a bad actor is. Acid value is traditionally up to 100 or a little over. Higher heating value, I show 16 here. Often we get 17 or 18, but our water value here is pretty high. Normally we get 25% water content, and this batch must have been one that it didn't work quite as well as usual. So we got almost 31% water. Carbon is 36, hydrogen 7.8, nitrogen 0.03. That probably comes from our blanket nitrogen that we run in our pyrolysis reactor. If there's any small leaks, it forces air out. So wood traditionally doesn't have much nitrogen coming out of it. And oxygen, 55%, 56%. That's very high, actually, even for ours. Okay, our boiler fuel, we've knocked the acid value down to 20. There is a standard for boiler fuel now from bio-oil. It doesn't require it has no standard on acid. The philosophy is if people want to burn it, they better harden their boilers because, and you can burn raw bio-oil, but this is much, much better to do right here because you're not going to eat things away quite as fast with this, with corrosion. The higher heating value is satisfactorily pretty high, 34. The water is 1.7. You can see we poured a lot of the water off. The carbon is doubled. The hydrogen is a little higher, and the nitrogen is increased. And that's, we're not sure why, except that when we pour the water off, none of the nitrogen goes with it. It stays with the organic fraction. The oxygen is 18.8%, and as I say, we'll never use this for transportation fuel, but it doesn't hurt to have oxygen in a boiler fuel. We get a highly combustible fuel. This yardstick, you can't quite see it. It goes really out the whole way. So this is a highly aerated burner we've talked about. They have some design of high aeration in this test burner that we just bought commercially. It's made for burning just almost anything, old oil. So we bought it for this purpose, and it works really well. Okay, we're going to switch now to our second fuel, esterification. This is an old technology, but we started with it and haven't gotten on it yet. Carboxylic acids with alcohol gives us a reaction that gives us esters and water. Unfortunately, because of the presence of water, if there's a high presence of water, this is a reversible reaction. So you perform the reaction for nothing if you can't get rid of at least some of the water. And complete conversion, if you just added alcohol to have this take place, you need 10 to 14 moles. That's a lot of alcohol. Most of the people who have done the esterification have used somewhere between 40 and 80%. That's a non-starter as far as we were concerned. We put 20% in at a max because there's no use doing this if you're going to put that much alcohol in. You can't afford to make it. I've already described this equilibrium problem, the non-reversal of the reaction. We are focused on keeping this alcohol addition down to make this a feasible economic proposition, or at least slow it so that you can get it to the place it wants to be used and use it. For boiler fuel, if it reverses a little, it's probably not so bad. The aqueous fraction is about 20%. When we use 20% alcohol, and we get about 55% yield of the boiler fuel, not quite as good as for olefination. This shows the product after distillation. Here's the water that we're going to pour off, thankfully, and get rid of some of it. Again, as I said, I'm not going to go through the bio-oil again, but I'm going to compare our biodiesel. I should have said MSU biodiesel because after it is distilled, it is 100% esters. It's 60% before we distill it, but 100% after. Our acid value goes from well, I'm not going to talk about bio-oil, but here's where we have our biggest problem. Our acid value is very high compared to the diesel standard. So we're not there except for a boiler fuel as yet. The higher heating value is there. We're above the standard. The water is not there. We have to work on that. We're good with the carbon, a little low on the hydrogen, real high on the nitrogen, which we may have to turn off our nitrogen blanket gas. It's not essential. And the oxygen is just a little higher than is required. So this is early in the study. So we have a ways to go, as you can see, but it is promising. This would be one of the early uses of biomass to make a biodiesel. And as you know, there's quite a difference in the cost of the raw material for bio-oil compared to biodiesel. We use mainly pine wood. These experiments are all based on pine wood. Okay, I've already used some examples where we do use a continuous stirred reactor, a small polar autoclave. We have a 500, a 450 milliliter and a 1.8 liter autoclaves. But we also have developed a packed bed. Now, we have come to the conclusion, most practitioners, there are many now who are trying hydroprocessing, and it very successfully produces a wonderful hydrocarbon mixture that usually has some percentage of, depending on the catalyst, gasoline, diesel, and jet fuel. And you get rid of the water. But we have become a little, and we're going to talk about these results, and we have spoken with people who have given up entirely on this technology. And we are not as optimistic as we used to be. When you start out, you think, and I've talked to people that were starting into this process, so they're going to hydrotreat, and they may have a big company, maybe 10 in-house organic chemists, and they're convinced, as I was, if we try hard enough, we'll solve this problem. Well, and we haven't given up, but it is a big problem. We are more in favor of larger tank reactors now, continuous stirred tank reactors. And what you'll see is that this can't be practiced right now. It's expensive, and as Dr. Spivey said, this has a very low liquid liquid flow. And as he said, if you want a small reactor, you want a high one. Well, all bio-oil that's hydroprocessed has a low flow, so you're going to need a big reactor. It's going to be expensive. We think, and usually you want no batch operations. Engineers don't want batch operations, but I'm not convinced that this won't be better, particularly since, as of now, this technology with hydrotreaters has not been shown to work, and they've been working on it 30 years. So this is our work on a packed bed reactor, where we are using, well, I'm going to report on both our packed bed reactor and our low hydrogen autoclave hydrotreating, and we get a high quality hydrocarbon mix from each. So hydrotreating with 100% hydrogen or lower hydrogen is going to turn your recalcitrant bio-oil into something that looks more like this. And you can see here you have your hydrocarbon mix, and here you have your water that you've driven off that's always necessary to get rid of. And your oxygenated compounds are the oxygen is replaced with hydrogen, and you have an upgraded fuel, really. Now, here's why the outlook isn't very bright. Now, there's probably a company out there that'll make me a liar, but of course, we're keeping a low profile. But Doug Elliott is the master of this at P&L, the OE. He's been doing it for almost 30 years, which when he started, he looks like a young man, but he's been doing it for quite a while. And his results, these are his results over the years of on stream, how long before deactivation of the catalyst. And that's the problem. The real problem is the catalyst deactivates in almost every case, and that's why people give it up, pull their hair out. His latest is this. He's gone to 100 hours, but his latest publication is here. He looks like he's reduced the variance of his performance, but he still only went to 91.5 hours before coking and clogging, total clogging of the reactor. We have the same problem, and we're not as good as Doug yet. We're much better than we were a year ago, I'll tell you that. But we still get coke flooding, and we can only go 28 hours ourselves. Here's our packed bed reactor setup, and we continue to plug away at it. And but we're not quite as enamored with this as we were. We're more, well, I'll show you the fuel qualities we get. The acid value for the place we are right now, which is early, is 13.4. Elliott didn't give his. We want to compare everything to Elliott, and we picked his best results out of his paper. He had several runs. But, and he didn't give us higher heating values, but given that he went up to pretty high yields, he probably has a fairly high heating value up towards the 43, 44. He has a probably pretty pure hydrocarbon mix, which we don't have at this time. The water of ours is 1.9. That lowers his higher heating value versus his 0.3. I think he had one that was 0.2, but we picked this as better than some other respects. I think it was the yield. His yield was 42. Ours is 38. Carbon, he beat us on the carbon, and the hydrogen's about the same. Nitrogen, we had none this time. And oxygen, we're still, probably a lot of this is water, but we still have a problem with our water, and we have a little ways to go on this fuel by this method. If we indeed do ever make it, that's. Okay, hydrotreating with low hydrogen. For this, we can do this with a hydrotreater, but it's a little discouraging to try because it doesn't appear to work for 100% hydrogen. For low hydrogen, we don't think it'll work either. So we are going to stick with increasingly larger and larger continuous stirred tank reactors, CSTRs. We've had some success with this, enough to file a provisional patent, and we use it for the hydrotreating stage. We've tried to use it, I'll need to explain that Elliott developed the method of hydrotreating first, followed by hydrocracking. The hydrotreating reduces it makes some hydrocarbons, reduces the water considerably, and allows for the later higher heat. It does the hydrotreating in a low temperature, 270 to 300. It allows for the second stage to be at a much higher temperature, above 300. So it doesn't polymerize this readily polymerized material. So that is now the way that everybody does it, as far as I know. Now, if we can reduce the hydrogen needed in the hydrotreating stage, and another thing that has been tried to be done over the years, and DOE had a special call a few years ago, is stabilize the bio-oil prior to shipment. And if you hydrotreat it first, and you need less hydrogen, instead of having a hydrocracker at the source, you might be able to do it with just tanked hydrogen, get it near the resource, and it's been pointed out what problem it is to haul this. Wood has as much water in it, it has mass, so you would like to not haul all that, get it as close to the source, stabilize it, not have it turn to gunk as you travel and transport it. Okay, here's our results. Our hydrogen is, this is with 100% hydrogen, this is with low hydrogen. Not much difference, 55.5, 51.6. Higher heating value, 34.7. Low hydrogen's actually higher. The water is 3.1 versus 2.7. Lower water actually. The carbon is about the same in the 70s. The hydrogen is about the same in the 9%. And the oxygen is actually lower in the low hydrogen. So about the same results. What this shows us, now we did these with the same time on stream. So we're putting a lot of hydrogen in versus not much hydrogen. And what that shows is for the hydrotreating stage, you don't need all this hydrogen. And we estimate that you can save, that you're using, now we have to do some careful measurements, but theoretically, as much as up to 80% less hydrogen for the hydrotreating stage. This is a comparison of the results if we compare and then we go on to 100% hydrogen for the cracking stage, and our acid value is below 0.1, not as good as diesel would like, but getting there. The higher heating value is 43 versus about 46 for the diesel. We still have a water problem, slight water problem, but we think we can see the light at the end of the tunnel from here. The carbon is about the same. Hydrogen's about the same. Nitrogen's a little higher for ours. Again, we may have to turn off our hydrogen blanket if that's what's causing this. We haven't gotten that far yet. These are early results. The oxygen's down to 1.5, which is not zero, but it's a step in the right direction, and it's done with a lot lower cost in the hydrogen resource. This is this mix analyzed by simulated distillation. We have trouble making enough to do real distillation at this point, but we found the simulated distillation estimates 55% gasoline range, jet range in the 30%, and diesel in the 15%, and nothing else. Some of our other hydroprocessing, we got some heavy fuels at the end that would need to be cracked, but we didn't get that with this method. Well, in summary, we've explored fuel making methods conversion from bio-oil to hydrocarbons and others, both traditional and new approaches. Olefination, it's our novel method to make a boiler fuel, and it has a pretty good heating value. It doesn't use a lot of olefins and not a lot of alcohol. Esterification of bio-oil gives us even higher heating value and the potential in the future to produce, which is our target. There's enough boiler fuels around. We want a transportation fuel that we can call a biofuel officially and sell it as such. We have progressed to production of mixed hydrocarbons with packed bed technology. We are improving, but no one has proven that this technology will ever work, to be honest with you. And we've pioneered the utilization of low hydrogen just over the last couple of months, actually, to conserve hydrogen in the hydrotreating stage. If we go to full hydrocracking with 100% hydrogen in the second stage, we get 55% gasoline, 30% jet fuel, and 15% diesel. Now, these aren't, I misspoke, they're not the fuels. They're the equivalent petroleum weights. So they're going to differ somewhat. Okay, I'm ready for questions, Casey.
Questions?
Wow.
One here. Thank you.
Thank you for a very nice talk. One thing you didn't mention concerns the catalysts. Are these traditional sulfided type catalysts or something different?
We have used some of the traditional catalysts, and if you follow Elliott's work, you'll know what some of those are. We also have our own proprietary catalysts for both HT and HC, which we prefer not to talk about at this time because we do have a provisional patent on those catalysts.
Right in front here, middle, say.
In your fuel number 1, where you're doing the olefination, you also include an alcohol. Is that really kind of a combination of your fuel 1 and fuel 2? You're doing esterification and olefination together?
We've found the alcohol is necessary to promote that reaction. If you don't use the alcohol, you don't get the results that you'd like.
Is the alcohol consumed and used to make esters?
As I showed, it makes ether primarily, esters. Yeah, it is converted to esters. But there's not much of it in there, but it does give you some esters. We have a paper published on that you could, if you want to get my card, I can send it to you.
One more question, if there is.
Thank you so much for your talk. I have a question about the hydrocarbons that you got. Did you characterize it?
I'm having trouble finding the... Oh.
Yeah, I was wondering if you characterized the mixture of hydrocarbons that you got more aromatics, or what type of hydrocarbons was in that mixture?
Well, which mixture?
You say when you distill and you got the gasoline, the jet fuel, and the diesel?
Yeah.
So did you characterize, like,
We
did you
did.
analyze?
We used, that was a...
what type of components you have
That was
there?
simulated distillation, actually.
Did you run GCMS?
We did, but I couldn't tell you the results right now. We do have a detailed hydrocarbon analyzer. Like I say, this is early in research in. I don't think we've gotten to that. Some of my colleagues are back there. Do they have a better answer to this question? Satish, if you stand up.
Yes, sir. We have done GCMS and DHA. Yeah, we got most of aliphatic hydrocarbons, like which are in the range of C7 to C12, and also we have some in the diesel range, like C13 to C17.
Because I thought like biodiesel, like you can get a lot of aromatics out of it, or but you said you got fatty acids, or?
He was talking about the hydrocarbon, not the biodiesel.
You asked regarding the question about hydrocarbons, right?
Yeah,
not
yeah.
biodiesel.
No, yeah, but yeah. Thank you so much.
Yeah, in our hydrocarbon fuel, like if you see the fuel number 3 and fuel number 4, there we have most of aliphatic hydrocarbons.
Thank you.
Thank you.
Very good. We'll stay with the schedule. We got one more speaker here.